All right, let's get started. So midterm 2 is Friday, right? I know. Kind of came quick, I think, at least for me. I don't know about you guys, but it feels like your last midterm was it feels like it was last week, but it wasn't. Yeah, I guess it was almost a month now, but yeah. Weird, time flies. Last week we talked about two things. Does anyone remember what they were? Heard it somewhere. Span, yep, that's one of them. So last week we talked about span, linear independence, yep. I'm just gonna put LI because that's big words, you know. Yeah, so I'll use Li for linearly independent and LD for linearly dependent. If you see that, it's just, I don't want to write it all out. So if we have two properties related to these, so say we have a set of vectors, I'm going to call it B, and I'm going to say my vectors are B1 through Bn. You'll see why I'm calling them B in a minute. But yeah. These are vectors, and we'll say they're a set of vectors in some vector space. So the first thing, if it meets these two criteria that I'm about to write, then we call this set a basis. Now, a basis is, it's a relatively important set because what it lets you do is it lets you take a vector space that is really complicated and turn it into something that's not complicated, like R3 or something, right? We've talked about like weird vector spaces, right? So we've talked about like P2, which is like the set of polynomials. We've talked about like M, I don't know, 3 by 3, which would be your 3 by 3 matrices, right? We've got a bunch of different examples of vector spaces, but they're very complicated compared to like Rn, right? We know how to work with Rn. We did that, that was unit 3, I think. So, you know, the idea here with the basis is that we're trying to convert something that's crazy into something that's not. Does that make sense? So for a set to be called a basis, it needs to have meet two conditions. So the first thing, you need B to be linearly independent. So we talked about how to find linear independence last week, right? The idea was you would do like alpha 1 B1 plus alpha 2 B2 plus all the way to alpha n Bn, keep writing B, equal to the 0 vector, and if the only solution to this system is alpha 1 equals alpha 2 equals alpha n equals 0. So if the only solution is the trivial solution, then your system's linearly independent. If you have more than just that trivial solution, then you would have infinitely many solutions, so your system is linearly dependent. The second test, or the second condition you need here, is that the span of B is equal to the whole vector space V. So in other words, I think in, like historically, you've heard that as like the set B spans the vector space or spans the entire space or something like that, right? That's what we're saying here. So the span of that set of vectors B is equal to the whole vector space. So using those vectors in B, you can reach the entire vector space, right? Does that make sense? So last time I talked about how like with linear independence, if you have just one vector, right, then that one vector is linearly independent because there's no way that you can write that one vector in terms of the other vectors. This is only one, right? If you add another vector, maybe it is linearly independent, maybe it isn't, but there's sort of like a point, a number of vectors after which if you add any more vectors, it's always going to be linearly dependent, right? You guys remember that talk from last time? And I said there was like a magic number. So as you add vectors, you reach a sort of magic number where after that point, it's always going to be linearly dependent. Before that point, it could be dependent or independent. And then we had the same idea with span, right? Where it was like, as you add vectors to a set, eventually the span of those vectors will equal the entire vector space. After which, if you keep adding vectors, it already reaches the whole space. So adding vectors isn't going to make it reach anything new, right? If it can already reach everything, if it already spans to everything, then adding more vectors isn't going to change that it already spans to everything, right? And that's after a magic number of vectors. And like I said last time, these two magic numbers are the same. We call that the dimension of the vector space. And we usually write that as like dim of V. So it turns out that, say that you have some, now I should mention, there's multiple bases for any vector space. You can find an infinite number of them. There's ones that are like relatively straightforward and easy to see. We usually call those like the standard basis. But you know, there's some that are possibly more difficult. So as like an example, in R3, this set is a basis, so 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's like your standard basis, right? Because like, you know, those are that's the easy option. But there's other options you could pick. You could also pick a basis that looks like this, 1, 1, 0, 1, 0, 1, 0, 1, 1. That's also a basis, and there's infinitely many other bases. You could pick, you know, I mean, really, you could pick like 2, 2, 2, right? Instead of ones, you have twos, right? Or threes, or negative ones, or whatever, right? So there's infinitely many bases. Does that make sense? But there's one key thing that's going to be the same no matter what basis you come up with. So maybe I ask everyone in the class to come up with a basis for R3. It's possible that we all come up with different bases. We all come up with something different. But one thing is going to be the same between all of us. And it's that basis is going to have 3 things in it for R3. If I'm asking you all to do R3, there's always going to be 3 things in it. And it turns out that the number of things in the basis is the dimension, which is the same as these 2 magic numbers, right? So the dimension is just the number of things in the basis, which in this case is like n, right? So if you have like 3 things in the basis, then the dimension is 3 in any basis. Does that make sense? So like if you're coming up with a basis, a quick check to make sure that you have a basis is to make sure that your basis has the right number of things, right? There's sort of a couple tricks to figure out dimensions. So for R3, or really I should say for like Rn, the dimension is just n. So it's like whatever that exponent is. For the set of say 2 by 2 matrices, or I shouldn't do 2 by 2, I should do like n by m matrices. The dimension is n times m. So you sort of just pull it right out. The one that's kind of a bit tricky is the set of polynomials of degree n. So this would be like, if this was P2, that would be like quadratics. It's n plus 1. Does anyone know why it's n plus 1? Yeah?
It's going to be just a variable like, example, P0, like it's just going to be a variable with a coefficient.
Exactly, right? So like you'd have like, in P2, a basis might be like 1x squared, right? So that'd be a basis. It has 3 things in it, but the little subscript is 2 because you have to account for that constant. Yeah? And this would be, again, like your sort of standard basis for P2, right? Any questions about any of that? No? Okay, so the nice thing about a basis, why do we care about this? It's because once you have a basis, you have a unique way to represent any vector in that vector space using a linear combination of those things. So like, as an example, if I had like, I don't know, let's say that this here is B1, say that this is B2, and this is B3. And let's say that I have a polynomial 2 plus 3x squared, sorry, 2 plus 3x minus x squared. I don't know. That is obviously in P2. It's a quadratic. But we can write it in terms of multiples of B1, B2, and B3. So we could write this as like 2B1 plus 3B2 minus B3, right? And maybe in this case it's like obvious, right? But if this basis was something more complicated, then maybe it wouldn't be. If it was something like this, right? How much of this plus how much of this plus how much of this, right? It's not so obvious. But using, like regardless, as long as you have a basis, so as long as it's linearly independent and it's the span of B is V, you can reach, or you can do this for any possible vector in your vector space. You can write it as like a linear combination of your basis elements. Does that make sense? All right, in that case, let's